Okay, so 4.6 talks about rank of a matrix, and every matrix represents a system of linear equations. So some definitions that I want to discuss in today's lecture is, let's just make sure I give you the right definitions. The row space. So I begin with an m by n matrix. There are three things that you will find. The row space, or two things. Row space of A will be a subspace of Rn spanned by the row vectors of A. We will notate this as row space of A. Okay, that's just a notation. The column space of A, which is a subspace of this spanned by the column vectors, we will call this column space of A. Good. Now, how do I find it? It's a very straightforward process. I give you a matrix. A is m by n. The row vectors are, can you write down the row vectors? And no work required, right? What is the row space? Combine them. And for this matrix, this will be a subspace. That's it. That's the row space of A. Good. Now, what are the column vectors? Oh, actually, what is the dimension of row space? Can you tell? How many vectors? How many vectors in the row space? Well, this is 1. This is 2. Dimension is? Are they linearly independent? How do we be sure? We will come to the basis of that in a bit. Even if you, okay, let's just talk about that for a different lecture. Dimension here is 2. Okay. What are the column vectors? Column vectors are just the columns. So I have this column, I have this column, I have this column. What is a column space? Combine them all. -1, 2, 0, 3, 2, 4, 1. Isn't this simple? What is the dimension of column space? 4 vectors. So finding row space, column space is like easy peasy lemon squeezy, right? Any questions? Now finding the basis for a row space and the basis for a column space, that's a whole different story. There are infinitely many vectors in row space and in column space. This is because the row space of A and the column space of A are the subspaces spanned by the row vectors and column vectors respectively. So what happens is you can add any linear combination, you can multiply a vector by any scalar, it will be in the row space. So it contains everything. It contains all linear combinations of these vectors also, right? Stems from just 4 vectors. Now, how do I make sure I have the optimum number of vectors in my row space and column space? I will make sure that they are linearly independent, and I'll make sure they span everything else. But checking for linear independence is too much work, right? You had to construct a matrix, you had to row reduce it, and see if you had an answer or not. What if I just began with a matrix? I have a matrix now. I want to find the basis for the row space. basis for the row space of a matrix. If a matrix is a row equivalent to matrix B in the row echelon form, then the rows of B, the rows, right? Just making sure that I give you the right definition. God, where is the, didn't bring the notes. Rows of B form a basis for row space of A. Okay. Consider this matrix A. Can you find me a basis of the row space? Well, you first, step one, you will row reduce. Row reduce A, what do you get? So I wanna get out all the redundant combinations. What if this row is a linear combination of these two? I wanna get out all the extra rows which can be made from the other rows of the matrix. That's what we're trying to do, right? Basis is the collection of linearly independent things. So we are getting rid of the extra rows which can be made zero. So row reduce this. Who's going to tell me the answer? So I have 1, 0, 1, 0, 1, 3. I could make this a 0. In next exam, you will be allowed a calculator. You're subtracting twice of that to that, right? This will be 0. This will still be 1. Twice of that, it will be. You see, I see a redundant row happening here. What will be the row reduced version of this? Make sense? So the basis is just the right amount of vectors. Basis of row space of A will be just the non-zero rows, because the last term, the last row could be made as a linear combination. 1, 3. Good? That's it. Now, how do I find the basis for column space? There are two methods. I prefer method 2, but I will teach you both of them for exams, whichever method you prefer. Basis for column space, you do the same thing. Find a basis for the row space of A transpose. So I'll find A transpose. A transpose which will be 1, 0, 2, 0, 1, 1, 1, 3, 5, right? Row reduce this, what do you get? I can just subtract this row. Okay, I see a redundant thing happening, right? 0, 1, 1, 0, 0. I'm not going to write the row operation. You guys are champions in finding the row operation that I'm using, right? Okay. The transpose, then transpose each of those vectors to get a basis for the column space. So I see two vectors, basis of column space of A. They say transpose them, right? So I will write this vector, the transpose. Makes sense, right? I'm talking about the column, so it should be 1, 0, 2. Now this method, if you like this method, be my guest. This is completely correct. You can apply this method in exam. I prefer method 2. Okay, any doubts so far? Anybody, any questions? Want me to explain again? Okay, good. Method 2 is my personal favorite. So you see why? Because everybody hates row reducing. I know you will get a calculator for exam 2. But even then, plugging in numbers, you can screw up. So you take the matrix A find its REF. And what was the REF of A? 101013. 101013000, and find the columns that have pivot. So this one has a pivot. If I go down and to the right, this one has a pivot. If I go down to the right, this one doesn't have a pivot, right? The columns with pivots in original A. Now this is the important part. In the original A are in your basis, are your basis vectors, right? So column 1 and column 2 will be in my basis of column space. So I got rid of the redundant columns.
You looking for the pivots in the REF version or the
original? Original one. No, I look for the pivots in the REF. Pivots only you can look in the REFs. Good question. You have to row reduce. The columns with the pivots. So if these two have pivots, these two columns in the original. Yeah, you see now? Yeah. Okay, so what are the column 1 in the original matrix? 102, right? That's the entry. What is column 2 in the original matrix? Do you notice something? They are the same. Method 1, method 2. Well, that's what we were expecting, right?
No, and in the REF that comes as 1, 1. And in the last diagram it comes as a 0. Is that okay, or do we need it like how we did it in Gaussian elimination? We needed 1, 1, and a 1.
But last row is 0. You cannot do anything from there, right? Gaussian elimination is what? If you end up with a row of zeros, you can't do anything, right? This makes sense? Okay, let's just stop this recording. And that's all I want to